Okay, so today we are going to start chapter 5, but let's go ahead and quickly recap 11.1. And I'm going to solve one exercise at the end of chapter 11, which is this 11.1. We are given some samples, information about some sample, and then we are asked to do a linear regression to predict something. Okay, so I'm going to solve 11.1, but let's first quickly go over what linear regression was. So, and we focus in this introductory course of statistics, we just touch very quickly on what regression is. We have a response variable and predictor variables, and we just consider one predictive variable, which is the univariate the form univariate regression. And if the response variable, the expected value of y given what x is, if you have this as a linear function of x, if you predict y as a linear function of s, this is called linear regression. And all we need to do is find these two constants. If you're going to have a line which has just, in univariate regression, it's only one x. If it was in multivariate regression, we try to predict a single response variable from multiple variables, and we would have more unknowns in this case. But here with just one variable, we have this line equation, ax plus b, and here a is like beta 1x plus beta 0. And our goal will be to find these beta 0s and beta 1 from given collected data. So we do it, find this beta 0 and beta 1 in such a way that in our current training data, the difference between the observed y values and the predicted y values after we find those beta 0 and beta 1 is minimal. But so we want to minimize a function. So we first find this difference between the predicted ones, which are these y1 hat, y2 hat, y3 hat. So if this is your line, you want to find a line that passes as close as possible to these points. And you measure the deviation from these points vertically by just looking at the difference between y coordinates. Okay, so as you can see, this is an overdetermined problem. If you have, in a line, we have only two unknowns. Only if you have 2 points in your data set, you can find a line that passes exactly from them. Okay, so exactly on them. So a line, a specific line will pass through two of these points, but unless your points are collinear, if you have more points, like 5, in this example, 5 points, it will be impossible to draw a line that passes through all 5 of them if 5 of these points are not collinear. And therefore, it becomes an optimization problem. Then you cannot find a line that passes through all of them. Why not find a line, find the best line that passes as close as to them? And the difference from these points are measured by these residuals. The squared difference, it will be the difference between the actual points y1 coordinate and the predicted ones. So we write the equation like this. So this is, we try to minimize that's why it's called least squares, the squared differences, sum of squared differences, least squared method, try to minimize this. So how do we minimize that? The yi's are a function of beta 0 and beta 1, x's are known, okay? So we are going to find these yi's by an equation beta 0. The only two unknowns will be beta 0 and beta 1 in this case. These are xi and yi are collected from our collected sample. So this becomes our equation to show the error, the sum of squared deviations, and our goal is to minimize this. How do you minimize a function like this? You take the derivative with respect to beta 0 and beta 1, and you find the equation normal and equate them to 0 to find these points. These become your normal equations. From this, your goal will be to find what beta 0 and beta 1 is. You write beta 0 in terms of beta 1 first, and then you plug in it in the other equation, which gives you this equation, in which a single equation where beta 1 will be equal to SXI divided by, sorry, yeah, SXI divided by SXX. Okay, so here beta uh, 1 will be equal to SXI divided by SXX, in which these SXY and SXX are the variables that, I mean, the constant parts that we can compute from these equation. This is like, SXX is like the the variance, the sample variance before it was divided by 1 minus 1 over n before it was divided by n minus 1, okay, or before it was multiplied by 1 over n minus 1. So as you can see, this is how we would, this would be a term that would appear when we would compute the sample variance for x. And this is the term, again, that will appear if we were to find the covariance between two variables x and y. So this is like called sum of cross products. This is called sum of squares. And if your data is available, they will be directly, I mean, if xi's and yrs are available, you know what x bar is, y bar is. These are sample average from both of these observations. These are easily computable by writing a simple for loop. If you have some data of size n, in linear time, you can compute SXX and SXY. After you have these two things, you directly have your linear regression coefficient. Beta 1 will be equal to the ratio of SXY, I mean, SXY divided by SXX. And beta 0 will simply be equal to beta 1 times your x bar subtracted from your y bar. So this is simply, I mean, writing a simple program to do least squares univariate regression is really simple. As you can see, all these things are computable directly from your sample data. This one too. Divide this one with the other one, you get beta 1. Multiply beta 1 with x bar, subtracted from y bar, you get your beta 0. And the equation becomes your predicted y hat will be equal to beta 0, the one that you computed, beta 1, x, whatever x is. So for a new x that is not part of your data, okay, this may be, you may give any x here and form this function, and you may predict what y is going to be. Okay, so you will have, this is your linear regression model that you create, this model is computed by using your training data set. This beta 1 and beta 0 are computed by using that sample that you have, those xi's. X bar and y bar is sample averages, so these are collected from those. And after you have this linear regression model, you have the power to compute y's given any x. Okay, so that's what linear regression is basically doing. Now, sometimes we may not be given, as we are going to see in exercise 11.1, we may not be given individual data points. We may be given some statistics collected from this data. For example, we may be directly given the correlation coefficient between x and y is this. The sample variance is this for x. The sample variance for y is this. So we may be given the variances directly from collected samples. So the measured statistics may be given to us, and these xi's, the individual data points, may not be available to us directly. But we are going to see that it's possible to, instead of the step 2 and step 3, instead of computing this SXX and SXY, so it's like a riddle, I'm going to we are going to see if a collected statistic like covariance and correlation coefficient is given to us, it's also possible to compute the linear regression model. So here are how they are related. If you remember what correlation coefficient was, so the covariance was directly this, and the correlation coefficient was the covariance divided by individual standard deviations, which was always between -1 and 1. Okay, the correlation coefficient tells us how strongly correlated two independent variables are related to, not independent, it doesn't show. If they were independent, the correlation coefficient would be 0. Okay, so two variables, how they are correlated with each other. This is what correlation coefficient is. And sample correlation coefficient is indicated by R. This is rho, the Latin letter. Uh, Sometimes we can use sample covariance and sample correlation coefficient to estimate the covariance and rho. So sample correlation coefficient is named as R, this small letter R, and this SXY we were using to compute B1. We are going to see that actually if the sample correlation coefficients are given to us and sample standard deviations are given to us, this is the sample standard deviation, Sx, Sy. As you can see, this is sample standard deviation. Beta 1, which was Sxy divided by Sxx, we see that it's simply could be rewritten as these ratios, these n-1s are going to cancel when we have this ratio. We can directly replace this with the sample covariance and sample standard deviations. So what in the end, here is the critical formula that we will use in this exercise is if the correlation coefficient is given to you, and if individual standard deviations from the sample are given to you, you are able to compute what B1 is. Okay, so if in the question, this is what will happen in exercise 11.1, instead of giving the entire data set to you as xi's and yi's, we will be given some values saying that, for example, yeah, let's go ahead and do the exercise and it's going to be clear. But B1 will be correlation coefficient multiplied by standard sample standard deviation of Sy divided by sample standard deviation of Sx. So this is what beta 1 is. How are we going to compute what beta 0 is from after this point? Beta 0 will be the same, y bar. You will be using the averages, sample averages or sample means to do that, b1 times x bar. So this was what beta 0 was, right? So you use correlation coefficient and sample standard deviation to compute B1, and then you use the sample mean to compute B0, and then again you're going to do the same thing. Y hat will be B1 x plus B0. You will have this equation to compute your prediction, to make your prediction. Okay, so this is what we will do in that exercise, and all these formulas, you don't need to memorize any of them, just know which ones you're going to be using. If you're given standard deviation and correlation coefficient directly without the actual data, you will be referring to this formula, this small formula right here at the end of this slide. If you're given individual data points, you will apply then this algorithm, first compute in a for loop, or you may write a program to do that quickly. Compute Sxx, Xxy, and then compute B1 like this, and B0 will be the same as the other, and then use that in your equation to predict what y is going to be. And we have seen that last time again, linear regression is not a bad method. It's very simple, but it's good actually. It's a really simple model. Instead of having complicated models, we could have polynomial splines that pass through all of the data. For example, there's cubic splines which have a cubic polynomial between every consecutive. So it's actually, spline is a collection. Like they are glued together at these junction points, but it's a collection of multiple third degree polynomials. When I say cubic spline, it's a third degree polynomial. It has four unknowns, ax cubed plus bx squared plus cx plus d. Okay, so imagine we had something like this to predict y hat. Y hat is equal to ax cubed plus bx squared plus cx plus d. We could have such kind of, this is not linear regression. We can call it maybe cubic regression. But in this case, you have four unknowns. If in your data set there are 4 data points in which a line does not pass through, it's possible to it's possible to have a cubic, a third degree polynomial to pass through all three of those, okay, for unknowns, for points. But what if you have 8 points? What if you have 9 points, 10 points? Are you going to use a higher degree polynomial? And higher degree polynomials do not behave very well. They behave erratically to move around here and here. So their prediction, as you can see, will maybe, it will overfit your data, but their prediction will be very bad in general for when they will not generalize. This is called generalization performance. You have a model on your training data set. How does it generalize to data points that are not seen yet? If their performance on not yet seen points are bad, it means that their generalization performance is bad. And a linear model like this, a simple linear model like this, has a nice generalization performance. And it's also possible, if you have 8, 9 points, this was what I was saying, it's also possible to, if you have many points, we will see this in 4th year computer graphics course. If you have many points, maybe 100 points like this, it's still to model the entire, it's possible to model a curve that, and not a very complicated curve, that pass through all these 100 points. And by cubics, by modeling between each adjacent points, you may write a cubic. Each one will be a different cubic. We will have multiple polynomials to make this model, but it's possible to make it appear as a single nice curve by having these extra constraints at the junction points. So this is not a topic of this class. As I said, we are going to see some techniques to solve this problem, finding nice low degree, third degree polynomials that pass through a bunch of points, 100,000 of them. You'll be able to do that. Okay, so this is, regression trees are, I think, quite different. I don't know, I have no knowledge of regression trees in detail, but I think regression trees may be a combination of decision trees and linear regression, maybe. That's just my guess. So I don't know what regression trees are, but usually what happens is that in decision trees, for example, you have a tree of decisions. By looking at different variables at each branching point, you make a decision. You branch to some of those trees, and maybe instead of making a decision based on just thresholds in decision trees, that's the classical case, you may maybe do some regression. If it may be a composition of regression and decision trees, but I'm totally guessing here, but from the name, so I don't know what regression trees are. So, but linear regression, there are different. If you're interested, you may read the rest of the chapter. There are different methods for regression, but that's the simplest case. The simplest form is linear regression. All right, so let's go ahead and solve this simple example, and then I'm going to start chapter 5. So here's the example. Let's see what is given to us, 11.1. Let's get, I'm going to erase this one, loss of noise, All right, so what we are given is the time it takes to transmit a file depends on the file size. Okay, so it tells us that we are going to do a regression. Given the size, we are going to predict time, probably. So this is what I understand from this, or maybe vice versa, but let's see. I think it says predict the time. So we are going to have an equation like this. The transfer time is equal to beta 1 file size plus beta 0. So as you can see, the time to transmit a file is related on the size of the file, and we are going to have a linear model to represent this relationship between size and time to transmit. And our goal will be to find beta 1 and beta 0, B1 and B0 from this sample. Now, we're not given any actual data, so we don't have a table of file sizes and transmission time. So in what in practice, this is what we would have. We would have a table that shows, okay, this is the size, and this is the transmission time. So we are going to have a certain sizes, for example, 10K, 15K, 50K, 15K, 45K, 1 megabytes. So we are going to have these size, and these will be my file 1, file 2. Each row will be a certain file, and my sample size, I will have n such files, and this is size, and I will also have time. So how much time it takes, for example, 1 second, 6 seconds, 2 seconds, 4 seconds, maybe 1 minute, I don't know. So here, usually we will be in the normally we would be given such measurements to us, and from this we would compute S bar, T bar, S bar, T bar will be computed from this, and then we would compute this SXX and SXY by using this S bar. And this time we will call it SS. Okay, here our X is this S, and we are going to compute as ST from this sample data. Now here in this question, we are not given the data directly, but we are given some additional information. Suppose you transmitted 30 files. So I know that my sample size is 30, n is equal to 30. I'm not going to be using this information probably in the question, but it's basically telling us that I collect this statistics from a sample of size 30 with the average size of 126 and standard deviation of 35 kilobytes. 126, 35. So what I'm given is that the average size is equal to 126 kilobytes, and the sample, it was the standard deviation, right? Yeah, the standard deviation, the sample standard deviation of this SS is equal to 35 kilobytes. So this is given to me, and let's continue. The average transmittance time was 0.04 seconds with the standard deviation of 0.01 seconds. So I'm also given T bar 0.04 seconds, and also the standard deviation of T is also given to me as 0.01. So these are given to me. If I'm given, for example, SS is given, ST is given, if I know the correlation coefficient between them, I would directly be able to compute B1. And after I know B1, since I know S bar and T bar, I would be able to compute B0 too. Then after that, I will have my model complete. So the only missing link here is the correlation coefficient between these two variables. And that's the last sentence in this first paragraph. The correlation coefficient between the time and size was 0.86. So R is equal to 0.86 here. So what was the formula for B1? B1 is equal to R times 0.86 times SY, which is SS here, ST, sorry, 0.01 divided by 35. Okay, so this is what B1 is. So let me see if I get the formula correct. Yeah, the predictor, the response variable standard deviation divided by the predictor variable standard deviation. So our response is time. So this is what B1 is. Let's quickly go ahead and calculate this. It's going to be a probably small number. Let me write directly. Why am I using my phone? I can write it here. 0.86 times 0.01 divided by 35, which is this number. So it's a small number. So let's copy this somewhere. Or let's leave it right here. That's my B1. And B0 is going to be equal to 0.04 minus this B1 times 126. So this is what B0 will be. So I multiplied this B1, which I computed. Let me just copy that and multiply it with 126, I subtracted from 0.04. So let's write it. So I copied this one 0.04 minus this number times 126. So, and this is my B0. So my equation, so what are we asked here? What are we try to predict? If we have a 400 kilobytes file, what will be the prediction transmission time? So what we are going to do is, here I computed, this is B0, this is B1. So I'm going to multiply this with 4. Oh, sorry, I didn't. So this is this B0? Yeah, this is actually B0. I did the equation. 0.04 minus this. So this is B0. So all I need to do is B1 times this one times 400 plus B0, which is this one. And that's your predicted model. It's going to take 0.11 or 107 if you're going to write this. So this is the time in seconds. Oh, it was 0. The standard, let me see, is the standard deviation 0. No, it's not the standard error of t-bar. It's information about the information given to us about the sample. So the average transmission is this, and the standard deviation of this. I remember, so I can see that why it's confusing, because in one of the questions I solved in chapter 9, I think, I interpreted a sentence that it was given like this. It's the standard deviation of the average. If you think it like that, it becomes the standard error. But usually when you're given some information, so about the sample, the sentence actually, probably I interpreted that exercise in chapter 9 incorrectly, because when we are given information about the sample, the average and standard deviation of the sample is given to us together. And in both of these sentences, it's saying with the average size of this and the standard deviation of this. So here, the term and, in the first sentence, it says and, so you understand that the average size of these 30 files is this, and the standard deviation of these 30 files is 35 kilobytes. Now, in the second sentence, this with, instead of saying and using with, you may again interpret it incorrectly, saying that, oh, it's the average transmission time is this, its standard deviation is 0.1. If you understand it like that, it becomes, as you can see, the standard error. Is it the standard deviation of the average, or is it the standard deviation of the sample, is what we need to make sure we understand here. By the way, my video is occluded. So, but I think that if it's not directly, specifically said to you in the question that it's the standard error, if in a single sentence it appears like this, you don't need to think too much about, oh, there's a with here, it has to be this. I mean, my interpretation in that chapter 9 probably was incorrect, because when we are given an information about a sample and it says average time is this and standard deviation is this, I think they just use with here just to not to repeat the and again. So just as a to write it in a more richer English way, they did this. Okay, so basically in this sentence, we are given the average, the sample average and sample standard deviation of some variable. So most of the time, if it's not specifically told us that that's the standard error usually is not given to us directly in these samples, because from the sample you can directly compute the sample average and sample standard deviation. Those are the most of the time the information given to you directly for a sample. So that's why we should take this 0.01 as the sample standard deviation of the variable t, okay, not t bar. I hope it's clear. So if the standard, so it's good that, it's very good that you asked this question, because I wanted to clear up that I didn't have a chance to discuss those exercises and how I interpreted some of those directly with you, but with the you gave us a chance to make this discussion too. Thanks for the question. So if you said something about the sample, you just take the standard deviation. It's ST. You should just treat it like this: the sample standard deviation of the variable, random variable t, not t bar. In that case, yeah, if it was the standard deviation of t bar, it will be, as you can say, standard error. But you shouldn't understand it like this. That's going too far in terms of interpretation of this sentence. So yeah, that's it. So we solved this question. It was, let's go back to this Chrome, and it's this many seconds. 0.107 seconds is the time it will take to transmit this file. So I think it makes sense, right? Or, I mean, this was the 0.0104 seconds. It's like the predicted time. Our predicted time is like 3 times larger than the uh, 3 times larger than the average transmission time, which is expected because our file size is also about 3 times larger than the average file size. So you can double check whether it makes sense to have the transmission time 0.1. Okay, because if you just mess up the formulas, change the positions of this sy and sx, you may get way off values, way off predictions. For example, if you got, like, for example, 0.00001 second to transmit that, it would not make sense, right? It should actually be, what we would get should be larger than this, about 3 times larger than this if you're using linear regression. If you get, for example, 1,000 times larger than this, there's something wrong there. If you get 1,000 times smaller than this 0.014 seconds as a result, again, there's something wrong there. So this is, you can double check with your intuition whether what you did was correct. And I think our model is correct, which is, now our model is this formula that I have written here. So replace this with any file size. What would happen if it is 800 kilobytes? It would be 0.2 seconds in our linear regression. So as you can see, it linearly increases with the file size. What will happen with a file of 126? If we have the exact average file size, what is it's 0.04. So it makes sense, right? That's also the average of our y bar. And but if you have, for example, 80 kilobytes file, it will take less seconds than 0.04. So this becomes our linear regression model, and we can use it to predict transmission time for different file sizes. I hope it's clear. Now this completely finishes chapter 11.1. And in this last 15 minutes, I'm going to do a small introduction to chapter 5, computer simulation and Monte Carlo methods. Here, what I want to mention, in the first part of this chapter, we are just going to see how we can sample single random variables from some distributions. First, we'll start with from known family of distributions. But you will see that the methods we are going to see, for example, how do we sample? There's an algorithm in the book. Actually, there's a typo in that algorithm. I'm going to also show you that. So here's chapter 5. So the first part is simulation of random variables. And here, when we say simulation of random variables, as I said, we will be generating single random variables from some distributions, from some target distribution. We're not going to cover the entire sections. We are going to skip this one. So generation of random vectors is not included. And special methods is not included. So just like we did in chapter 11.1, in which we just talked about univariate regression, in this 5.2, we are going to focus ourselves on single random variables. We are not going to generate random vectors. It's not that complicated, but we are going to leave 5.2 at that. And from 5.31, we are not going to talk about forecasting lengths and areas, but they're all Monte Carlo integration, but they're also not that difficult to cover. We are going to see how we can use Monte Carlo simulation to estimate some difficult probabilities. And if I remember the story correctly, um, let's actually search for that on the webs, and let me also verify my knowledge on that. Monte Carlo method, Monte Carlo method, hospital, solitaire. How do you spell solitaire? Yeah, yeah, yeah. It's this one. So let's. Yeah, it was. Yeah, I remember the person's name, Stanislav Ulam. So, so here the Monte Carlo was. So this is the Monte Carlo method was thought up by mathematician Stanislav Ulam. I think he was also working at that time, if I'm not mistaken, in the Manhattan Project. He's also one of the people who worked on the Manhattan Project. And worked with von Neumann, by the way. Yeah, Manhattan Project. Yeah, this was Stanislav Ulam, so he's the father of Monte Carlo method. So he participated in the Manhattan Project. So they were trying to figure out very complicated interactions between atoms. How the uranium atom, for example, depletes in certain situations. So he was, and here the Monte Carlo method. So he was thought up by mathematician Stanislav Ulam, who was playing solitaire on his hospital bed while recovering from a surgery, and named it after his uncle who had gone gambling to Monte Carlo. The Monte Carlo casino was in Monaco. If you're a follower of Formula One, you would know that there is it's like an underpassage that goes under the Monte Carlo casino in the track on the track. So that's a place, that's a casino in Monte Carlo. So usually gamblers at that time, certain probabilities are really difficult to compute. And he was trying to figure out. So I mean, these scientists are really they like puzzles. So he was just trying to figure out while playing solitaire, what is the probability given just a shuffled deck of cards? What is the probability that you're going to get yourself a solution, a solved solitaire at the end? What is this probability to, given all these different deck of cards? You start. I mean, most of the time, you're just playing. I mean, you can automatically play the solitaire game, but depending on the arrangement of the cards, sometimes it will be impossible to solve that solitaire. So he was wondering, what is the chance of having a solitaire solved? And then when he tried to figure this out, mm, analytically trying to solve the probability, he saw that it's really difficult to mathematically just give an equation for this solitaire problem. So what he did was, okay, why do I do that? Just I play solitaire maybe 1,000 times. The ratio of solitaire games that are solved may tell us the probability directly. Okay, I mean it's maybe an approximation of that probability. So this is the idea. If we have and they use this Monte Carlo method to find probabilities of very difficult atomic interactions between complicated things. So the and underneath the Monte Carlo simulation, what we need to do is we need to have a way to generate some random numbers from certain distribution. For example, you need to have a way to first generate those single random variables from their individual from their distributions, and then you put them together into a simulation. How many of them you want to have, things like that. You and then count the favorable outcomes to predict the probability that will be very difficult to figure out uh, by writing some by mathematics itself. Okay, so a very important component of Monte Carlo simulation is to generate random numbers. And back in 1940s, 50s, we didn't have computers, and they didn't have these nice MATLAB Octave Online that they could use. Uh, and we will see in the first part how we can simulate random numbers from some family of distributions. And all the methods that we will see here is going to use a single function, a uniform random number generator. Okay, imagine we have a function. So in most languages, for example, if you're going to program in C, C++, whatever Monte Carlo simulation you want to do, there's this rand function. So the rand function gives you uniformly between minimum integer and maximum integer, as I believe. So it gives you an integer, but it's easy to turn this into a uniform number, a standard uniform number, which is going to be between 0 and 1. Okay, so this is the PDF of a standard uniform random variable. Okay, as you can see, this is the PDF, and any number between 0 and 1 is equally likely going to be generated. So if I tell you we will be using in Octave Online, this rand function, the single rand function gives us Octave Online. Let's go to Octave Online, Octave Online net. So we will be using this rand function. Whenever you type rand, it takes no parameters. It gives you a number between 0 and 1. And these are some random numbers between 0 and 1. And any number between 0 and 1 is equally likely. So they're standard uniform. By using these numbers, is it possible to generate random numbers from any distribution? That will be our goal in the first part of the chapter. By using these random numbers, for example, can you simulate a Bernoulli variable whose success rate is 0.8? Okay, a variable which just takes zeros and ones, sometimes 0, sometimes 1. Okay, so you will be generating, for example, 0 and 1 or 1, but I want that 0 or 1 to be generated with 0.8 success probability. So you're going to generate ones and zeros. And since these are random variables, for example, I want to generate 100 Bernoulli random variables. In these 100 random variables, Bernoulli variables, I want the success rate to be 0.8, which means that roughly 80 of them are going to be ones and 20 of them are going to be zeros. But you want this 100 data points to be a random sample. You cannot just write a C program saying that, okay, let's have first 80 of them 1 and the last 20 0. Okay, that's a Bernoulli variable. We don't want exactly 0.8. I mean, if you take a random sample from that Bernoulli distribution, maybe you would get 87 of them are going to be 1, maybe 85, or maybe 75 of them are going to be 1. So it's going to be different. So you want to simulate a Bernoulli variable with success rate 0.8. How can you do that? By using a uniform random variable. Think about this. It's not a very difficult. The chapter starts with this first problem with a uniform random number by using, if I give you this rand function directly, think about how you would generate a Bernoulli variable with success probability 0.8. And sorry about this. I'm getting notifications from something else, but yeah. Their relative distances to something. So let's see the relative distances to what we're looking for, to 0.8, for example. The only parameter I have is the probability of success is 0.8. Okay, so that's my probability of success. When I generate these random numbers, by using each of these random numbers, I'm going to generate, I want to turn it into 0 and 1. Okay, look at this, for example. Oh, sorry, not P. So let's generate a random number. 53, 64, 0.4, 37, 36, 42, 18, 89. So can you convert these standard uniform random numbers to Bernoulli variables? Exactly. You can do it if the rand result is above 0.2, accept it as 1, otherwise 0. That's perfectly fine. But you don't need to. You can also do what the book does is we can instead of subtracting that 0.8 from 1, we can directly use that 0.8 in our decision. For example, when I generate a random number, If it's less than 0.8, I generate a Bernoulli variable 1. If it's greater than 0.8, I generate a Bernoulli variable 0, which means that uh, I divide my entire standard uniform area with the 0.8 threshold. I will generate ones when it falls here. I will generate zeros when it falls here. What is the probability to generate 1? 0.8. What is the probability to generate 0? 0.2. That's your Bernoulli variable. So that's basically, we will just say generate a random variable, whatever it is. If it's less than 0.8, this is going to be 1. Or greater than or equal to 0.8, or maybe less than or equal to, I don't know. Since this is a continuous random variable, whether you're going to have equalities at these boundaries or not, it's continuous. It doesn't matter that much. So it's an infinite equality to 0.8 directly is an infinite, very small, infinitely small probability. So where you're going to put that equality is really like an implementation decision. But if it's greater than or equal, let's call it. If it's greater than or equal to 0.8, generate a Bernoulli variable 0. You see, this way, and what you're saying, Berat Furkan, is also correct. Why do we have the threshold here? Your solution was to have the threshold here at 0.2 because probably you want to have 0 first, because 0 comes first before 1, right? So 0, if it's less than 0.2, generate a 0. If it's greater than 0.2, generate a 1. And that's perfectly correct too. So with either methods, by just using a uniform random generator coming from standard uniform, we were able to simulate a Bernoulli variable. That's our first thing. We were able to generate a Bernoulli variable by using, so for example, if I do this, rand less than 0. Rand less than p. Let me write this. Look at this. Right now what I'm doing, it's since this less than p is like treated, returns 1 if it's true and returns 0 if it's false. It's just simple thing. I have my uniform random generator and p is 0.8. I will have ones, two zeros one after another. Would you generate something like this if you were to generate your random variables manually? Probably not, right? I mean, we would just say, okay, I need to have 8 ones and 2 zeros. You would probably want to distribute those zeros between ones. But when you're having some random numbers, zeros can, wow, look at this. 4 zeros, one on top, right, one after another. And I will have lots of ones on the long run, but less zeros. But it's possible to have 4 zeros one after another. So that was a very small probability, but in a random sample, it is still possible. All right, so with this simple equation, I have a Bernoulli. I can generate a Bernoulli variable. On Thursday, we're going to continue. I'm going to stop quickly now. On Thursday, we're going to see things like this. If I have a probability distribution, if this is the probability density function that I have, for example, look at this probability density function. Does it look like any family of distribution that you know? No. It has 4 modes, 4 peaks like this. If this is the PDF of some random variable, and maybe it's between 0 and 800, this is what x is. Okay, can you generate random numbers that follow this probability density function? I want, for example, 350 is going to appear with more probability, but also 450 is going to appear with some probability too. So if this is some arbitrary PDF, can we generate uniform, not uniform, can we generate random numbers, random x's from this P distribution that will follow this PDF? This is what we're going to see, and I think this is really remarkable. I mean, just by using a uniform random number generator rand, doing this. We'll see this on Thursday, but yeah, since the method we're going to use is going to be very simple. We're going to generate random points between in this rectangle. If the point is under this curve, we are going to accept that and point it out. If the point, we're just going to generate random points in this rectangle, uniform random points within this rectangle. And only the points that are under this curve are going to be reported as simulated variables, which makes sense, right? I mean, in regions where PDF is large, the probability to be under the curve is going to be large, so it's going to be reported. Otherwise, it's not going to be reported as a variable. Look at this genius idea. I mean, which this is called rejection sampling, and it's one of those sections that we're going to cover. Okay, the method is very simple, but we will be able to generate random variables from any distribution, for example, with rejection sampling. All right, so that's it from me for today. I will stop recording.